Hey guys, how's it going? We finished up the midterm exam. I can tell you this, the good thing is the first half of this course is slamming. I told you all that, man. We had a ton of stuff. Atomic theory, into the calculator, moving into resistors and color code, then moving on into Ohm's law. All this stuff, schematic symbols, everything. That's a lot. A whole lot of stuff in a short period of time. But the good thing is from here on out, all we have to talk about is how things are connected. And there's only two ways to connect things together. You're going to connect them end to end, or you're going to connect them side by side. That's the only two ways to hook things up. Now, there will be combinations of those two, but bottom line, basically, that is the only two ways to hook things up, end to end and side by side. So, that being said, what we're going to talk about first is the end-to-end connection. Now, as we go through this, understand that this applies to anything that can be connected in this fashion. The only component that we've learned so far is the resistor, so that's all we're going to be using in the analysis of these circuits. But all these concepts we're going to talk about hold true, no matter what component there is that you're connected. So the end-to-end connection. First of all, end-to-end connection. End-to-end connection, when we connect two things together like this, we seem to have components that are following one right after the other in this one path for current flow. Now that's going to be the key thing to understand about series, that there is only going to be one path for current flow. And I'll let that slip too, but when things happen one right after the other, it's series of events, a baseball series. Well, this type of connection is called a series connection. So these are series circuits. So what I want you to know is as we go through this and I write up on the board, I'm not going to wait for everybody to write it down. You know, that's what that little pause button is for on your phone. So just pause, write the notes down, because you're going to want to write them. You know that's how it works. You can look and watch this all you want to, but if you don't write these notes, it really doesn't go through your brain. We talked about that. In your eyes, got to go through your brain to get down to your hand. And then once it gets to your hand, it goes back into your eyes. And so it's about no, it's not 9, but there's a bunch of different exposures that help it stick with you. So go ahead, pause, and write this stuff down. So we're talking about series circuits. And a series circuit is an end to end. End-to-end connection. I know that glares up there, but end-to-end connection. So that's one right after the other. So the important thing to remember is that it does only create one path for current flow. So we want to make sure we get that. And you have to understand, right? When these electrons are flowing, I told you, it moves like marbles in a garden hose. Well, the garden hose is full of marbles. As soon as I push one in, they all shift at the same time, and one instantly falls out the other end. This is the nature of electron flow, or at least an idea or a picture you can have when it comes to it. And if you think about this, if I push a marble in, if it only goes in so far, or it goes in a certain speed, well, all them marbles there are going to be moving in that same speed. Also, if I push 3 marbles in, there's going to be 3 marbles falling out the other end. that means that all the marbles in there are moving at the same time, at the same speed, everything. So the deal is, if I only have one path for current, that movement, if I only have one path, well, I'm only going to have one current. I mean, think about a one-lane road with one slow driver all the way up to front. How fast are the rest of the people behind them going? The same speed that that one driver is. So the amount of flow is going to be the same everywhere in that one path. So we need to know, first and foremost, is the amount of current is the same everywhere in a series circuit. Now look, over here on the agenda, I told y'all we're going to do introduction to series circuits. Now we've got this thing called Kirchhoff's series voltage and current laws. Well, yeah, that's Kirchhoff series and voltage current laws, but the deal is, it's as simple as saying the amount of current flow in a series circuit is the same everywhere. Well, that's what Kirchhoff's current law says. So Kirchhoff series current law is just another way of saying the current is the same everywhere in a series circuit. Okay? So we know there's current. It's one value of flow. Now, pause, write that down. Here we go. All right, so that takes care of current. Now, what about voltage? Remember the big three, and that's what we've got to focus on these different types of connections. And what happens to the big three? Well, we know one is that current is going to be the same everywhere. You know what? As a matter of fact, if I say IR1, that's the current through resistor 1. If I say that's 2 amps, well, if it's a series connection with R2, if it's a series connection with R2, you know what I know? Right off the bat, I know current's the same. I'm going to write the same number down in an analysis. See, that's what you need to remember. Yeah, the flow is the same, but also when we're analyzing these circuits, current is the same. What about voltage? Well, if we look at this, okay, you got to know and remember what voltage is. What is voltage? Well, voltage is the difference in potential between 2 points. Difference in potential between 2 points, and if it ain't the same 2 points, it ain't going to be the same voltage. Let that sink in. Voltage is the difference between 2 points, and if it ain't the same 2 points, it ain't the same voltage. Simple as that. Might be the same amount, but it ain't the same voltage. So, voltage is the difference of potential between 2 points. So let's say between this point and that point, I have a source of 10 volts applied. This is a series circuit. Got my source, got my path, got my load, and of course, well, it doesn't have a control device, but it doesn't need one. So here's the deal. If I measure the voltage across this source, and this source is connected to these 2 points, well, the amount of voltage that I'm going to have between those 2 points is equal to that source voltage. So I have 10 volts between there and there. Now, how about this? How about from here to here? Will I have that same 10 volts? Well, I'll tell you this. This point right here and this point, electrically that's considered the same point because they're connected directly together. So I can stick my meter probe here or I can stick my meter probe there because it's the same 2 points. Doesn't have any components between those 2 points. One solid line. Well, between this point and that point, I've got a component, so I know that this point and that point ain't the same point because I got a component between them. Well, my question is this point and that point the same point? Well, no, I got a component between the two, so it can't be. So if I measure 10 volts from this point to this point, am I going to measure 10 volts from this point? No. Because this point and that point are not the same point. Now, I will tell you this. I do have voltage applied, and I do have resistance, and I do have a path, so I'm gonna have current. And Ohm's law tells me that if I have current through a resistor, I'm gonna have some voltage there. Now, is it necessarily gonna be half and half? No, it's not. The difference is, remember the whole proportionality thing about Ohm's law of voltage and resistance being directly proportional. If I got a big resistor and a little resistor, well, I'm going to have a big voltage and a little voltage. Remember that? So it doesn't necessarily divide in half, but let's say, and I'm just making these numbers up to make a point. Let's say I have 3 volts across that resistor, resistor number 1. Well, I got 10 here, right? And if I put $10 in my pocket total, and I only spent $3 here at this store, how much should I have left to spend at that store? Well, money's money. So I know that I'm going to have, and here's the kicker, the rest of this voltage. You see, this applied voltage in series is divided up between the components. Now, when I say divided up, I don't mean mathematically. I mean divided up like a pizza. If I cut a pizza up in 8 slices and I put 8 slices back together, I'm going to end up with a pizza. So if I take this pizza, cut it up, I'm going to put it back together, I'm going to end up with the pizza. It's as simple as that. So voltage is divided among the individual, and the sum, which means the answer to an addition problem, the sum of the voltages in series is always equal to that applied voltage. And you know what? There's that Kirchhoff voltage law again. It says, well, blah, 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 but bottom line, the individual voltages will always add up to the total applied voltage. That's Kirchhoff's voltage law. So, So the Kirchhoff laws are voltage divides proportionally, and the sum of the individual voltage drops is equal to the applied voltage. Okay, so take and pause this and copy it. All right, this is the last little tidbit for this one. So we need to cover resistance. So current's the same everywhere. Voltage divides, or what about resistance? Well, we got to know how to find the total resistance. So if we have a circuit, or let's say I have a resistor right here, and that's R1, and that's 20 ohms, okay? Well, ask yourself, how much resistance do I have in that circuit? 20 ohms. That's good. Y'all are good. All right, so now let's say I put another resistor in the same path as that 20 ohm resistor. So I had 20 ohms and I put 10 more. So how much resistance total do I have in that circuit? It's good. 30 ohms. Whoo, y'all are good. Y'all are good. And so, wait, let's try this one more time. If I had another resistor and it was 5 ohms, what would my total resistance be? 35 ohms. So look, how do you find total resistance in a series circuit? That's right. You add them up. You take and add up the individual resistors. So this is the last little tidbit we got to get. So RT, resistance total resistance, RT is equal to R1 plus R2 plus R3. So in this little section, what you need to beat into your brain, series circuit, end-to-end connection creates one path for current flow. With one path for current flow, current is the same everywhere in that path. And voltage divides in a series circuit, a little bit across each one of them. They all add back up to the total. And in order to find total resistance in a series circuit, you take and add the individual resistors together. Now, if it's a kilo ohm resistor, do I have to enter the exponent 3? That's right, I do. I got to enter in that exponent 3. So everything that we've learned up to this point, folks, holds true. If I'm asking you for voltages, you better put a V behind your answer. If I'm asking you for current, it's an A. So everything still applies. New concept, making connections. This is end-to-end called series. Current's the same, voltage divides, and you add up your resistors. Got that? Okay. See you in a minute.